Hello everyone, my name is Mingjia and I'm a master's student at Beijing Institute of Technology. This is a recorded talk for my AAAI paper, VBLC, Visibility Boosting and Logic-Constraint Learning for Domain-Adaptive Semantic Segmentation under Adverse Conditions. Here is the outline, and now let me introduce this work. Recent years have witnessed the prevalence of deep learning-based methods in fundamental vision tasks like semantic segmentation. However, most studies are centered around datasets consisting of clean images, making them vulnerable when deployed under adverse weather conditions like fog and rain. Therefore, transferring models trained by clean images to adverse weather conditions is critical to building a trustworthy perception system. Domain adaptation is one of the best options to solve this problem. In domain adaptation, knowledge is transferred from a well-labeled source domain to an unlabeled target domain. The core idea of domain adaptation is to narrow the gap between source and target domains. To enable domain adaptation to adverse weather conditions, a common practice is to utilize the geometry correspondence invasion to form a pair of clean and adverse images. However, the collection of paired images is demanding, and extra efforts are required to label the clean images that are freshly collected. Therefore, we managed to cancel the reliance on correspondence and propose to achieve adaptation in an unsupervised manner. Enhancement of image visibility is a well-explored research area. A significant body of works has discussed the mechanism behind the formulation of adverse conditions like fog, rain, snow, and night. The core of poor visibility image enhancement is to model the formulation of poor visibility for a possible solution. Through physical models, one can narrow the domain gap in the image level, which is favorable to domain adaptation. Multi-target domain adaptation or generalization aims to transfer knowledge from a single source domain to multiple target domains. The core idea behind this setting is to fully exploit source knowledge to simultaneously benefit multiple target domains. Previous attempts mainly focused on performing adaptation to a target domain under one certain adverse condition, but in reality, the adverse condition can be hybrid in practice. Consider the huge diversity of adverse weather conditions. It is thus more valid to view all adverse conditions as part of a hybrid target domain than to handle them as discrete target domains. Now I would like to explain the motivation of this work. In this work, we enable the domain adaptation from images under clean weather conditions to those under adverse weather conditions, namely normal to adverse domain adaptation. Compared to previous methods, we try to reduce two main constraints. Firstly, we drop the constraint on the geometry correspondence between paired source target images to ease the burden of data collection. Secondly, we handle different weather conditions with a unified model, which is much more practical than training an individual expert models for each weather condition. Without paired images as weak vision, we are now face an even larger domain gap. To narrow this gap, we employ physical models to boost the visibility of target images. Further, to handle images under different weather conditions in a unified way, we modify the original physical models to enhance the images dynamically. We then propose a visibility boost module to cater to both these needs. Despite the effectiveness of the visibility boost module, the gap between enhanced target images and clean source images is still hard to eliminate. We thus propose the logic-constraint learning scheme to tackle the problem of overconfidence commonly seen in self-training process. To sum up, in this work, we propose visibility boost module along with logic-constraint learning to enable high-quality unsupervised domain adaptation to hybrid adverse conditions. In this part, let's take a closer look at the proposed method, VBLC. In normal to adverse domain adaptation, we have a labeled source domain with clean images and a non-labeled target domain under average conditions. The source domain and target domain are of different distributions, and we assume that there is no correspondence information provided between such two domains. Therefore, the objective is to learn a neural network with parameter phi to achieve good generalization performance on the target domain. First, let me introduce our Visibility Boost module. This slide presents ASM. It is a physical model to describe haze formation. The ASM is chosen as it can model the veiling effect commonly observed in fog, rain, and even snow scenes. And we assume that such an effect is a major obstacle to a clear vision. The transmission map can be estimated from the observed image as the slide shows. However, direct utilization of such estimation may corrupt the enhanced image, and we propose to add an adaptive coefficient omega s to modulate the haze extent. Here, the coefficient omega s is an adaptive value calculated from the saturation of the image, which is thus also applicable to other weather conditions. Separate discussion should be given to the nighttime images. Researchers have found that reverting nighttime images can be viewed as hazy images, so we can use the ASM to handle the reverted nighttime images. And we ought to design a pair of inverse switches at both the head and tail of the VBM to extend our method to nighttime. So this is the ultimate visibility boost module, and it can enhance the images under different average conditions in a unified way. Now let's move on to Logit-Constraint learning. Although the visibility boost module is capable of reducing the domain gap in the input space, the intrinsic difference between clean source images and enhanced target images can still lead to the problem of overfitting to the wrong target pseudo labels when applying a self-training scheme. First, let's take a look at the cross-attribute loss commonly used in self-training based methods. Here we have K classes. Y is a one-hole pseudo label, or the ground truth label. P is a model prediction from the logit Z. And cross-attribute loss can be given as follows. Suppose the label Y gives the JTH class, and there is a gradient of cross-attribute loss to the JTH element of the logit. From this gradient, we can find that when we train with the cross-attribute loss, the prediction would overfit to a given label, and if a label is wrong, the result is disastrous. To solve this issue, we propose the Logit-Constraint learning loss, and here is the formulation. We can see that, different from the cross-attribute loss, we normalize every logit with its L2 norm. Again, if we divide the gradient of this loss to the logit's JTH element, we could get this result. In this formula, the gradient is made of two parts. The former part is the same as that in the cross-attribute loss, and the latter part is key to resolving the problem of overconfidence. If the prediction is confident, then the latter part is close to zero except for the JTH class. Now let's take a look at its coefficient. If the prediction of the JTH class is very much confident, then this term should be close to 1, and the over gradient should be close to 0. However, if the prediction is not that confident, the coefficient of the second term should be smaller than 1, and there is still space left for optimization. Otherwise, if the prediction is unconfident, the coefficient of the latter part should be larger for a possible candidate class K, and therefore the optimization on the JTH element of the logit is slowed down by other possible candidates. Through analysis, we can find that Logit-Constraint learning could theoretically reduce the problem of overconfidence. Here is the framework of our method. The target images are first enhanced with the visibility boost module to get boosted target images. Then the two pairs, namely the source target pair and the source boosted target pair, are trained with class mix augmentation and logic-constraint learning. The whole framework adopts the student-teacher architecture to stabilize training. Note that in the test process, the VBLC boost module is no longer needed, as the model is already trained on target images. Here is the formulation of the logic-constraint learning loss, and below are the three losses in the training process. Note that the loss involving target images or boosted target images are weighted by the proportion of confidence target predictions, namely this lambda. And all the samples are trained with logic-constraint learning, including the source samples. This is for the consistency in the training process. And here is the overall training objective. The model phi is trained on all three losses. For the sake of clarity, we summarize the training algorithm in this slide. Now let me show you the experimental results and in-depth analysis. We first compare our VBLC with the state-of-the-art domain adaptation semantic segmentation methods on the task cescapes to ACDC. Both datasets are collected in reality, so our method's leading performance on this task best shows its superiority. To elaborate the capability of our method, we also experiment on the adaptation from cescapes to the mixture of focus cescapes and range cescapes. And our VBLC consistently provides good segmentation results. To showcase the flexibility of our VBLC, we further extend our method to object detection and multi-domain adaptive segmentation. And here are the results. Although our VBLC is not specially designed for these tasks, the performance gain is still considerable. We then perform an emulation study on the task of cescapes to ACDC to explore the importance of the components proposed in our method. The results show that both the VBLC boost module and the logic-constraint learning contribute to the overall performance, which confirms their necessity. We also visualize the convenience distributions of models trained with cross-entropy loss and our logic-constraint learning loss on the ACDC validation set to justify the effectiveness of the proposed loss. The left chart shows that the model trained with cross-entropy loss tend to yield high probability, while one trained with our loss is relatively conservative. The right chart shows that the wrong predictions made by cross-entropy loss trained models are mostly of high probability, while the model trained by our loss never make overconfident predictions. From these two charts, we can prove that our logic-constraint learning loss is an effective solution to overconfidence. This slide visualizes the loss landscape of models trained with cross-entropy loss and our loss on the ACDC training set with ground truth. The landscape is given by calculating cross-entropy loss for both models. The blue region in the figure shows that the model trained by our logic-constraint learning loss had more potential to achieve better prediction quality. Let's now view the visualization of segmentation results on the ACDC validation set. And it can be seen from the figure that the prediction of our VBLC is much cleaner and more accurate than the baselines. Now let me conclude this talk with some remarks. First, we tackle a more realistic and challenging task of domain adaptive semantic segmentation under adverse conditions without the aid of extra image counterparts as reference to form a clear adverse image pair. Second, we achieve a better adaptation by making adjustments at both ends of the network. The visibility boost module is proposed to narrow the visibility gap in the input space, while the logic-constraint learning is included in the output space to handle the overconfidence issue. Finally, we will justify the effectiveness of our VBLC and explore the mechanism behind its success by extensive experiments. The paper and code are available for our work. Please feel free to contact me if you have any questions. In the end, I would like to thank my collaborators and my advisors. Thank you everybody for your attention. Thank you.